Hi, welcome to Classical Physics, and this is our last lecture, and we'll be talking about friction, and we'll be doing some spring examples. So we'll just jump right into it, into our classic block on a surface, and as you're aware by now, we have a weight, which equals to the mass times the gravity in SI units, and we are doing a normal force opposing that, and this time we have a force P that's pushing against this block, and now we are not ignoring friction. In the previous examples we've been kind of ignoring friction just so we could focus on the other applied forces. Now we are going to signify our friction force opposing our pushing force, and that is going to be signified by F. So we are going to graph what happens here when this is being pushed. So there's some midpoint here, and on one side we have equilibrium, and then we've got this axis will be our frictional force, and this action will be our pushing force. On the other side of this equilibrium, we'll have motion. I'm going to draw this, and then I'm going to explain what I am drawing. So we'll be coming up, we'll hit this, we'll come down, and then we'll be constant. Well, actually, let me do it this way so that, okay, be pushing till we hit this equilibrium, and then once we hit here we will break into motion. Okay, so this is what's happening. So as you go along, as your pushing force increases, let's just say you're starting from the block having no forces applied to it other than its own weight and the normal force. So as you apply force, and as your force increases, your friction force, which is opposing that pushing force, also increases. So during this whole region, this blue region here, you are in equilibrium. The block is not moving, and you're increasing your force, and as you increase your force one for one, you have an opposing friction force that matches that pushing force until you hit this apex here, which we are going to call our friction maximum. So once you hit this friction maximum force, you can also call it your maximum static friction. So once you hit your maximum static friction, it breaks loose, right? The block breaks loose, and then you see a drop in your friction force. And once you see a drop in your friction force and you're moving the block, you still have friction, but now this friction, put it in the color green to match it, but now this friction will denote it as K. So this force of M, and you can sometimes call it S, or force static, friction static friction, friction static friction, sorry about that. So you're increasing your force, and your friction force increases linearly until you break loose of you reach a maximum limit of your friction, and it breaks loose, and then it starts to slide, and then you are now in your dynamic friction range to where you still have friction but your block is moving, right? I hope that makes sense to you. So let's see what that looks like with an equation. So we have some force, and this force, I'll write it in blue so we don't confuse it with just So we have this maximum force or static force. That's going to be equal to the coefficient of static friction multiplied by the normal force. So what is this coefficient of static friction? Basically, it is a constant that gives you the relationship between the two surfaces. Like different materials have different coefficients of static friction. Like steel will have a lower coefficient of static friction than maybe a tire on asphalt, right? So those different material changes will give you different coefficients of static friction. Now, that applies to this area. So that means that's going to be the force it takes to break loose that friction. Now, when you're talking about this area, that constant friction as you're pushing it, that we'll use a different constant called the coefficient of dynamic friction. So this is top one, blue is static, green is dynamic. So dynamic coefficient of friction is the friction that is obtained between those surfaces with the object moving. So that's static and dynamic friction. Hopefully explained in a way that you understand it. So let's go ahead and dive into some examples. First one will be pretty quick and simple. Second one's going to be a little bit more involved. First one will be just like the diagram that we showed. So we have a block on a surface, we have an applied force, we have a weight, and we have a normal force, and then we have opposing friction. So let's just say we know our coefficient of friction. Let's say our coefficient of friction is 0.5. Now we want to know, this is friction here, we want to know what force must be applied to overcome friction, right? And let's say this thing here, weight equals 50. Oh, actually, here's what we'll do. We'll call this has a mass of 50 kilograms. Okay, so what's our first step? Our first step is we actually have to know the weight, not just the mass. So our weight equals mass times gravity, and that 50 times 9.8 is 490 newtons. All right. So here's what we know. We have some force P, and so what we have to know is, or what we have to realize is, P from the previous example we had from the force M or the force static, that is going to be the same in this example, because whenever I reach this maximum static friction force, that means it's going to break loose from the surface to allow the object to actually be pushed, right? So I'm reaching that apex to where now if I hit that point, the block is going to start moving, right? And so I want to know what that force is, which is what the question asked us, what force must be applied. So if I apply the same force that it takes for the block to break loose, then these two are the same, right? Okay. So let's go ahead and write that. So now P will equal the coefficient of static friction, because we're at rest and we want to know what it takes to break it loose, times the normal force. So what is the normal force? The normal force is equal and opposite of the weight, which equals 490 newtons. So our force it takes to move the block is going to be 0.5 times 490 newtons. And what is it, 245? So P equals 245 newtons. And that will be the force it takes to get the block started moving based on that coefficient of friction. Right? So that's how friction works in basic static example with a flat surface. Now let's do a little bit more complicated problem. Well, actually, what I'm going to do is, let's see. Okay, yeah. So we're going to do an inclined plane. Now the block is resting on the inclined plane. And this angle is theta. So I'm actually going to explain something to you before we get into some things. So, if you have this situation, then let's draw our free body diagram. So this is representing the block. You have a weight, which is mass times gravity. You have a normal force, right, that's coming back up to this. And then you have an opposing friction force. Now, this is, I don't know if I stated this or not, this is in static equilibrium. Meaning this block is not sliding down the plane. The block is just sitting on the plane. So, the block is still, it's on the plane, not material still, but it's sitting still on the plane, not moving. Static equilibrium. So, given this free body diagram, we can actually rearrange this normal force, right? And we can draw it this way, right? We're just taking it along the same thing it was in. And then we can do a right angle. Oh, whoops. Normal force. And then we have our triangle here. So, oh, I apologize. Okay, so what we can do is we can rearrange this normal force and draw it like this. And then if we come out at a right angle, this is a right angle, we make a little triangle with our weight and our normal force. We know that this will be shorter, this normal force will be shorter because it's going in out at an angle, and this is just a straight line. Well, that was a terrible explanation. So we can rearrange this normal force and bring it just like this. It's still the normal force. And then we can come out to the mass times gravity, or weight. So what does that show us? Well, first of all, what is this angle? This angle, theta, is the same angle as this theta. If you picture this triangle, we're like this, and you do the geometry, this is the same angle, same theta. So what does this tell us? Why is this useful? Well, this means, we'll stay in green, why not? So this means that mass times gravity, or weight, times the cosine of theta is going to equal your normal force, right? Mass times gravity is right here, vertical down. And so that's the hypotenuse of the triangle I just made. And so mass times gravity times cosine of that theta will be my normal force. And so because we're in static equilibrium, what is this force here? That, if you look at the direction, is our friction force. Therefore, mass times gravity times the sine of theta equals our friction force. What can we do with this relationship? Well, if I wanted to know the force it takes to break the static coefficient of friction and move the block up the inclined plane, I would need to know, just like the last example, what my maximum force would be. And so that would be force, frictional force, is going to equal the static coefficient of friction times the normal force, right? Which equals the static coefficient of friction, and we substitute in our normal force that we just saw, mass times gravity times cosine of theta. So now that's our frictional force. We have this relationship. But if you look, we have two equations for the same unknown. So now we can say, if we just combine these two and say the mass times gravity times sine of theta, which came from right here, equals the coefficient of static friction times mass times gravity times cosine of theta, which came from right there. Now, mass times gravity cancels, and you're left with sine of theta over cosine of theta equals the coefficient of static friction. Let's bring that on over here. Sine of theta over cosine of theta is tangent of theta equals coefficient of static friction. Whoop, that last one sucked. Okay, hold on. There we go. There we go. So the tangent of theta equals the coefficient of static friction. Therefore, on an inclined plane, in static equilibrium, now that is a key point. That means it's not sliding down. In static equilibrium, on an inclined plane, your coefficient of static friction is equal to the tangent of theta. So that is a rule that you should probably just memorize. I mean, you can derive it quite easily if you've forgotten it, but that's how you can come up with the coefficient of static friction. And that's kind of how people do it, right? So like if there's an example that we don't know what the static coefficient of friction is between two materials that we're going to experiment with, we can set this little inclined plane up, right? We can put our object on it. If we know, we just keep increasing the height of this ramp basically, until it starts to slide. We record how long we end up being and how high we end up being, and then we can then we know the static coefficient of friction between those two materials. All right. Now let's go on to springs. Okay, so if we're talking about springs, we got to talk about Hooke's law. And before we explain that, let's say we have a spring and a box or a block or whatever. And so this spring has a particular spring constant. This block has a particular mass. And let's call this x0. Now, afterwards, what we do is we compress that spring to x1. And this is where we were, right? So we were here. Same block, same spring constant. What is a spring constant? A spring constant is a value given to a spring, and it's its force over a particular distance. Meaning this: if you purchase a spring, you may have a spring constant of 100 newtons per meter. Per meter. What that means is every meter it supplies 100 newtons of force. So if I go 2 meters, it's 200 newtons of force, and that's along the compressible length of a spring. Or if you have a tension spring, it's the exact same thing. If you expand it and the spring constant's 100 newtons per meter, then every meter adds 100 newtons of force. And this goes in with the equation force. This is Hooke's law here. The absolute value of force equals the spring constant times the absolute value of delta x, and this delta x is the distance or the deflection of the spring. And our spring constant is given to us when we purchase the spring, or whenever you buy a spring, you'll know the spring constant. Now, if you have a spring and you don't know the spring constant, you can work backwards, right? You can apply a known force over a known distance, and then you can solve for your spring constant if you don't know the spring constant, right? So it'll work both ways. So let's do a quick and dirty example. Let's say there's some force that's applied to this mass, the same example you see up at the top, and maybe some force is given, and we have a spring constant of 100 newtons per meter, and we are traveling 1 centimeter, right? Well, first of all, what we'd have to do is we would have to convert centimeters to meters, because we have to have like units here. So we have 1 centimeter. And then just like in dimensional analysis, 100 centimeters in a meter, which is 1 over 100 meters, right? And so force equals 100 newtons per meter multiplied by 1 over 100 meters. Force is going to equal, our hundreds cancel, right? 1 meters cancel, Newton, right? So our force that is being applied to the block to compress the spring 1 centimeter or 0.01 meters is 1 Newton. And so that also means that the spring is applying 1 Newton of force to the block if it's being held in place. Right? Okay, looks good to me. So, just like I said, we can do that with solving for the force that's applied, and we could do the same thing if we knew the distance and the force but didn't know the spring constant. I'll just make up an example on the fly here. Let's do the same scenario. This time we'll say this block has a tension, has an expansion spring, and it's being stretched. And so if we stretch this spring, we don't know where the spring came from, we don't know anything about the spring, but we know that we're some distance here that we're going to call 0. And now our delta distance from 0 is, let's just call it 2 meters. 2 meters, and we know our force will actually have some, let's say we put a little force gauge or here, and we're measuring our force equals 300 newtons. So we're pulling 300 newtons, and we moved this object 2 meters, expanding this spring until it stopped moving. This is as much as we can get out of it, right? So knowing those two things, we can solve for the spring constant. So same equation. We know 300 newtons equals some spring constant times 2 meters. And we also know, just why you want to keep this in meters here, a Newton, if you remember, 1 Newton equals a kilogram times a meter per second squared. So we want to keep this meters when we do the distance here. So what is the spring constant? Well, it's pretty easily seen that we divide our distance, 2 meters, from our force. So 300 divided by 2 is 150. 150 watt though, right? I'm going to put a space here. I want you to think about this. If you have to pause this to think about it, what is the spring constant? Units, you can kind of think about a previous example and that'll tell you, but why is it that, right? What I want to get across is you can treat units kind of like you do numbers. And so we had newtons and we divided by meters, right? So we end up with 150 Newton per meter is our spring constant. That may have been extremely self-explanatory to a lot of you, but maybe it wasn't. So I just want you to understand the importance of putting your units down when you're writing your equations down, because it will help you understand the reality of what you're doing. So when you're doing the spring constant, if you don't have your units, and if you say, hey, my spring constant's 150, it's just as ambiguous as not saying what unit you're in when you're given a length. So you want to put your units down. It helps you relate to what's actually happening. Alright, so we have went through friction and we have went through some basic spring problems. And later on, as you get deeper into physics, you'll see more complicated scenarios that may involve the combination of some of these springs, and you can apply some of these springs in like series or in parallel with one another. And I'm going to just show you what that does to the spring constant really quickly. So say you have one spring and you have another spring tied to the same object in parallel, right? That means just like a circuit is parallel, they're not tied. Well, let's just do this. This would be an example of a series spring connection. So series, parallel. Okay, so what does that do to the spring constant? If it is in parallel, the spring constant final, or total, or however you want to call it, is just equal, let's call this one K1, K2, is just equal to K1 plus K2. So that was simple enough, right? So if you have two springs tied to the same object, but the springs are not tied in series with one another, they're in parallel, they're to some datum and then they're to the object. They're in parallel. The spring constants can be added together to be a new spring constant value. But if you are in series like this, now your spring constant final is, well, it's actually not just the spring constant final, it's 1 over the spring constant final. So 1 over the spring constant final is going to equal to 1 over the spring constant of 1 plus 1 over the spring constant of the other one. So this will look a lot like circuits if you've ever gotten into any circuits circuit courses. Can't think right now. So if you're in a parallel setup, you can just add the spring constants together. But if you're in a series setup like this, it's the reciprocal. It's 1 over the final spring constant is going to equal to 1 over the spring constant of 1 plus 1 over the spring constant of the other. And then you can do 1 over that value and get your spring constant. So that's an important rule to follow, and that may help you whether to determine in a design what you want to do given a certain design constraints on what you have. You may be able to more clearly calculate what you want to get based on what you have. That's a really vague and ambiguous statement right now if you haven't gotten into any mechanical design or anything like that. But if you do, this is an important rule to remember. Alright, so I think we've covered just about everything I'd like to cover with friction and with springs. So I really do hope you've enjoyed this course, and I hope that it's helped you prepare either for a college course that you may be taking, or to help you, maybe it's a supplement for a course that you're currently taking, or for your children or whatever. And but yeah, so I hope you've enjoyed it, and maybe I'll put out future courses in the future, but thank you again.